Good morning to all of you. I am Bhupender from BSc Chemistry Honors final year. Today we are going to discuss about electronic spectroscopy. As we already know that a molecule can have several types of energies, rotational energy, vibrational energy, electronic energy, etc. When energy is absorbed by a molecule, it can undergo rotational, vibrational or electronic transition depending upon the amount of energy absorbed. All these types of energies of molecule are quantized. That is, there is only discrete rotational, vibrational or electronic energy level available to the molecule for excitation. Each electronic level is associated with a number of vibration levels with less energy separation, and each vibration level in turn is associated with a set of rotational levels with even lesser energy separation. Rotational energy level have the minimum separation, then vibrational and then electronic. Rotational energy transitions take place in microwave region, vibrational transitions take place in IR region, and electronic transitions take place in visible and UV region. When a molecule absorbs energy in a microwave region, the transition in rotational energy level takes place and rotational spectra are observed. Vibrational spectra are obtained by the transition of the molecule in vibrational energy levels when it absorbs energy in infrared regions. So the electronic spectra of the molecule are observed in visible and ultraviolet region of the electromagnetic spectrum. Born-Oppenheimer approximation. The total energy of the molecule is composed of contribution due to electronic energy, nuclear energy, and energy due to vibrational, rotational, and transitional modes of motion. For real molecule, it is not possible to treat these energies independent of each other. But in practice, these energies are considered separable and independent of each other. This is because these energies differ by a large magnitude. This approximation assumes that since the nuclei is several thousand times heavier than the electrons, therefore the nuclei are expected to move much more slowly than the electrons. Thus, nuclei may be assumed to be stationary while the electrons move at much faster speed relative to them. Therefore, according to Born-Oppenheimer approximation, the electronic motion and the nuclear motion are treated independent of each other. Hence, the transitional motion of the molecule as a whole and vibrational and rotational motion of the nuclei within the molecule may be treated separately from the motion of the electrons. Therefore, according to Born-Oppenheimer approximation, the electronic energy may be treated separately from the transitional, vibrational, and rotational energy of the nuclei. Transitional energy is not quantized while the other energies are quantized, that is rotational, vibrational or electronic energies. The magnitude of electronic transitions is the most, so the time taken by electronic transition is less. So the total energy is given by the sum of rotational energy, vibrational energy and electronic energy, and all these energies are independent to each other due to their magnitude difference, which is very high. Type of molecule exhibiting electronic spectra. All the molecules exhibit electronic spectra due to change in the electronic distribution level. Homonuclear diatomic molecules such as H2 and 2 extra do not give rotational or vibrational spectra but show an electronic spectrum. The nature of electronic band spectra. The electronic spectrum is produced when the molecules jump from lower electronic level to higher electronic level. The light from visible or ultraviolet region is capable of inducing transition in the electronic, vibrational and rotational energy levels of the molecule. Thus, the electronic spectrum of the molecule results from transition between electronic energy levels accompanied by transition both in vibrational and rotational energy levels. As mentioned in the previous section, according to Born-Oppenheimer approximation, the total energy of the molecule in the ground state is given by the sum of electronic energy, vibrational energy and rotational energy. So the difference can be calculated by the difference in these energies of higher excited state and state. In the term of a wave number, we can write it as a del E by Hc, and del E is the sum of the differences of the energies in higher excited state and ground excited state. These energies differ from each other in magnitude by a thousandth time. Any change in electronic state is accompanied by similar changes in vibrational and rotational energy levels. For an electronic transition, there is no specific selection rule for the change in vibrational quantum number. So del V has no restriction. As a result, transition between a lower electronic states to higher electronic states, the vibration level can change to any state, that is from V0 to V1, V0 to V0 of higher excited state and others. The, these rotational excitations result in line and produces a fine structure within each band. As a result, the electronic spectra is quite complex, constituting of series of band groups. Despite their complex nature, the electronic band spectra of molecules are preferred over type of spectra. This is because they are observed in visible and ultraviolet regions and can be conventionally recorded and studied. Potential energy curves for electronic states. For a diatomic molecule, the average electronic potential energy is a function of internuclear separation and is represented by Morse potential function given as potential energy is equal to my dissociation energy into my 1 minus epsilon raised to power minus beta into my r minus re whole square. A potential energy curve for a diatomic molecule is obtained by plotting electronic potential energy against the internuclear distance between two atoms. A typical potential energy curve of a diatomic molecule is shown in figure 2. Each electronic state is made up of vibrational level indicated by horizontal line and are indicated by appropriate vibrational quantum number. Each vibrational level is associated with rotational levels. It is clear from the curve that potential energy decreases as the internuclear distance between them is decreased. We can see from the graph that as the internuclear distance decreases, the potential energy also decreases. The probability of finding the molecule in the vibrational level is indicated by probability distribution curve in various vibrational states. According to quantum theory, for V equal to 0, the molecule is most likely to be found at the center of the ground level vibrational levels, whereas for higher levels, the probability of finding the molecule is high at the extreme position. We can see it from the figures 3 that probability of finding the electron in V0 is in center, but in higher vibrational levels the probability of finding the electron is at extreme positions. So internuclear distance in excited state is larger than that of the ground state. This is because bonding in excited state is weaker than in ground state. It is clear from figure 4 that the upper state curve is also represented by Morse curve similar to that in the ground electronic states. However, the two curves differ from each other with respect to the position of minimum in the potential energy curve. The minimum energy point for excited state is at a larger internuclear distance than in the ground electronic states. This is due to the weaker bonding in excited state. Frank-Condon principle. During an electronic transition, all type of transitions from the lower vibrational level are allowed to any two of the higher vibrational level. Even then, it has been found that all such transitions in electronic spectra are not of same intensity. The relative intensity of lines in electronic spectrum may be explained in terms of Frank-Condon principle, which said that an electronic transition takes place so fast that a vibrating molecule does not change its internuclear distance appreciably during the transition. In other words, the principle states that the movement of nuclei is negligible during an electronic transition. This means the time required for an electronic transition is so short that the nuclei do not have time to change their position appreciably. The principle is closely related to Born-Oppenheimer approximation. Therefore, during absorption of radiation of the molecule gets excited to different energy states represented by the different potential energy curves. Thus, every excited molecule can be considered as a molecule which has a slightly different Morse potential energy curve. The internuclear distance in the excited state is the same as in the ground state at the time of electronic transition. Hence, according to Frank-Condon principle, there is no appreciable change in internuclear distance during the transition. There are no selection rules for del V, and the transition will occur at the position where wave function is maximum. For quantum mechanics, we know that the molecule is at the center of ground vibrational level of the ground electronic state. If the internuclear distance in ground state and excited electronic state is equal, then the most probable transition is from V0 to V0. Hence, if the internuclear distance in excited state is slightly greater than the ground state, then the most probable transition guided by Frank-Condon principle is from V0 to V2. This transition has maximum intensity. The other transition have lesser probability and thus have lesser intensity as compared to intensity of 0 to 2 level of vibrational of higher excited state. These less probable transitions occur from first excited vibrational level of ground electronic states. Electronic spectrum of diatomic molecule. Here we can see that there are different cases. In case 1, the internuclear distance in higher excited state is equal to the internuclear distance in ground excited states. So the maximum possible transition, most probable transition is 0 to 0, and this gives maximum intensity, while the other transitions have lower intensity. In case 2, internuclear distance in excited state is slightly greater than internuclear distance in ground electronic states. So now the most probable vertical transition is from V0 to V2, while the other transitions have less probability. In case 3, the internuclear distance in excited state is highly greater than the internuclear distance in the ground state. So the transition corresponds to this gives a continuous spectrum due to dissociation of the molecule. Because the molecule dissociates, the atoms thus formed can have any value of kinetic energy, so such transitions are not quantized and thus a continuous result. Here we can see images of different graphs in which figure 6a image is in which internuclear distance equal of both the states. In B, the internuclear distance of higher excited state is slightly greater than the internuclear distance, and the most probable transition is 0 to 2. And third one is the continuous spectrum. The vibrational transition accompanying the electronic transition give rise to vibrational fine structure. The fine structure provides information about the excited electronic state of the molecule. Calculation of dissociation energy of diatomic molecule. The electronic transition B2 takes the molecule to an excited vibrational state having energy more than its own dissociation energy. Hence, the molecule will dissociate. Similarly, when the molecule is excited into upper state E2, which has no minimum and is unstable, it undergoes dissociation. The kinetic energy of resulting atoms in the excess energy that required to dissociate the molecule. It may be noted that the dissociated atoms are produced in electronically excited states. Hence, the total energy of dissociation of atom produced the excited electronic state is excess by an amount called the excitation energy as compared to the dissociated atom produced in the ground excited state. Thus, this excited excess energy must be subtracted from the dissociation energy in the excited states. Some terms which we use in electronic spectroscopy. Parity. Parity is used when a molecule has a center of symmetry, like a homonuclear diatomic molecule. The sign of wave function of molecular orbital may or may not change when it is inverted through the center of symmetry. The term parity is used for molecular orbital of homonuclear diatomic molecule if it refers to the behavior of the orbital with respect to inversion. We start from any point of the molecular orbital and travel equal distance through the center of the molecule to the other side. This process is called inversion. If the sign changes, that is called even parity and denoted by G from Garrett. And if it sign changes on inversion, it's called odd parity and is called ungarrett. Heterodiatomic molecules do not have center of inversion, so they do not give any parity because they don't have any center of inversion. Here we can see some images. S and S overlap, center of inversion, and this gives garage on bonding, while in anti-bonding it's give change inside signs and gives a garage, ungarrett and odd parity. Similarly for the p orbitals. Multiplicity of an electronic state is given by 2s plus 1, where s is total spin quantum number. If all the electrons in the electronic states are paired, then s is equal to 0 and it is called singlet state. If there is one unpaired electron in the electronic state, it's called doublet. If there is two unpaired electrons, it's called a triplet. For example, H2 positive ion has only one electron, therefore S is equal to 1 by 2 and its multiplicity is 2 and it's called doublet. Term symbols for diatomic molecules. We write term symbols for different diatomic molecules and this gives various information us about the molecule. Here we use spin multiplicity, Garrett ungarrett, center of inversion and symbol used for the total orbital angular momentum also. Selection rules for electronic transition. Selection rule. This rule states that the spin multiplicity should not change during a transition. That is, del S should be 0. So singlet to singlet are allowed, triplet to triplet are allowed, while singlet to triplet are forbidden transition. Total orbital angular momentum selection rule. This rule states that del L should be plus minus 1 are allowed transition, whereas other transitions are forbidden. Parity selection rule or laboratory selection rule. This rule states that the transition of opposite parity are allowed while the transition of same parity are not allowed. Restriction on symmetry change during transition. During a transition, the symmetry change is not allowed and for taking a transition, symmetry should be same. Type of molecular orbital involved in electronic transition are sigma, pi and a lone pair. Sigma transitions are occurred by normally saturated compound, pi transitions are occurred by unsaturated compounds and a lone pair transition, that is from n energy level, takes place by heteroatoms compounds which contain heteroatoms like nitrogen, oxygen, sulfur, halogen, etc. It may be noted that there are no excited state non-bonding orbital associated with n orbital. From we can see figure 8, sigma bonding has the lesser energy, then pi, then n, then pi star, then sigma star. So transition take place between these energy levels.